Hello and welcome back to High Peak Education. I would like to perform now a lecture on electromagnetic induction. This is for a calculus-based Physics 2 class, and this is chapter 13, at least in that class. Now, the idea of electromagnetic induction is that we're going to use magnetism to produce electricity that was not there in the first place. So, namely, induce electricity from magnetism. And in fact, as we're going to see, it's from magnetic flux. So let's get started. Let's talk about magnetic fields versus electric currents and the concept of magnetic flux. So we've seen previously that electric currents produce magnetic fields. But can magnetic fields produce electric current? So if you've seen my earlier intuition video, hopefully you saw that if you have a magnet, say like a bar magnet, and it moves through a conducting loop, it is going to produce an electric current. And that's based on a law that I'll present on the next slide. So what is electromagnetic induction? It's going to be inducing voltages, which are EMFs, and thus electric currents through the motion of magnets. Notice an induced EMF is related to how the magnetic flux, capital Phi subscript B, changes in time. Now notice magnetic flux is going to be defined in a very similar way as electric flux was. Notice that if we have a magnetic field, B, and it's moving towards an area, and let's say this loop has an area of A, and let's say that this magnetic field is going like so, and there's some angle between the magnetic field and perpendicular to that loop area. The magnetic flux will be BA cosine phi. Now this diagram shows theta for the angle, but I'm going to call it phi because phi is going to be between 0 and 180 degrees, and it's going to be the smallest angle between the magnetic field and the area vector. So, magnetic flux, think of flux as how much flux is through. In other words, how many lines move through an area, and that's kind of the idea. How much does this area sort of catch those magnetic field lines pushing through? So, as with electric flux, magnetic flux is proportional to the number of field lines entering versus leaving an area. The units for magnetic flux is going to be Teslas times meters squared, because that's the units of magnetic field and area, cosine of phi being a dimensionless number. And by the way, the technical unit for that is actually called Webers. So Webers is not often used. A lot of people still just write Teslas times meters squared. But in any case, you will see that unit out there for magnetic flux. Okay, so now let's take a look at Faraday's law of induction. This by far is going to be the most important equation in chapters 13 and 14, and a central equation in electricity and magnetism, and it's going to be the equation that we'll use most often when we talk about electromagnetic induction. So, imagine we have an extended magnetic field object. What is the total magnetic flux? Well, first of all, it's going to be the integral across this surface. So if you have some extended surface and there's a bunch of dA vectors, and the angle between them is theta or phi, between B vector and dA vector, you should just add them all up. So the total magnetic flux is the integral of B dot dA. Now, by the way, this integral is the area across a surface. So it might or might not be a closed surface, but you should integrate across the surface. This is really a surface integral. And here's the idea behind Faraday's law of induction. Any change in the magnetic flux in time will produce an EMF. In other words, if the magnetic flux is not constant with time, if it's a non-steady magnetic flux, not necessarily magnetic field, but magnetic flux. So, in fact, the magnetic field could be changing or several other things. that will produce an EMF. Remember, an EMF has units of voltage. So here is the basis equation of Faraday's law. It's capital epsilon, that's the EMF, is equal to minus d phi sub b dt. That is the opposite of the time rate of change of the magnetic flux with respect to time. Let's think about the units. The units for magnetic flux should be Teslas times meters squared. When we're taking a time derivative, we divide by seconds. Remember what a Tesla is. It's a Newton per Coulomb per meter per second. And still, here we still have meters squared per second. If you work all that out, you get newtons times meters over coulombs. But wait a minute. Newtons times meters, that's joules. Joules per coulomb is energy per charge, that's volts. Who knew? So it turns out a changing magnetic flux with time is indeed a voltage. Now, by the way, if you have, say, n identical coils or turns or loops, Faraday's law is just modified to be capital N times larger. So we just multiply by capital N on the right-hand side. So let's make some important notes on Faraday's law. So it turns out Faraday himself first noticed electromagnetic induction when turning a switch on and off when another coil was nearby. I actually showed this in the intuition video if you've already seen this. Faraday had something like a wire wrapped around an iron core and two sets of coils, but only when he would close the switch or open the switch was there a change in the magnetic flux through the one coil, and that induced a changing magnetic flux on the other coil. And he actually saw a blip of current, and then it went away very quickly. Note that a moving charge, which creates a magnetic field, is not sufficient to create an EMF. So notice, just because charge is moving doesn't mean there's going to be an EMF. Notice that moving charges create magnetic fields, but we actually have them have the magnetic flux changing in time. The magnetic flux and thus the moving charges must change in time. So this is a non-steady situation. This magnetic flux, as I've said several times, must not be constant with time. If the current at hand is the change of moving charge, so like a current, think of an accelerating charge or changing a current in time. So you could imagine that if it's a string of charges, then we can induce electricity from magnetism if the current is, let's say, increasing or decreasing in time. Let's have a look at Faraday's law of induction, but let's think about the methods 1, 2, and 3. Now, method 1 will be changing magnetic field in time. Method 2 will be changing area with time. And method 3 will be changing loop orientation, so that's that phi with time. So notice we're going to break up each of the three pieces of the parts of magnetic flux and examine them for their time rates of change separately. So using the definition of magnetic flux, Faraday's law can be stated as minus d by dt of BA cosine phi. So an EMF can be induced only when the flux is changing in time. Since the magnetic flux depends upon BA and phi, we can induce the EMF three different ways. Change the magnetic field strength, B within a coil or many coils with time, is the first one. So let's imagine what you hopefully saw me perform in the intuition video. Notice that if you have several coils here and a bar magnet, and you plunge the magnet upward, there's a velocity, and thus there's a change in the number of magnetic field lines moving through this loop as a function of time. So if you move that permanent magnet into or out of the conducting coil, you will change the magnetic field strength, induce a voltage through relative motion. Now notice I say relative motion because you can actually move the magnet up through the loop, or you can move the loop down through the magnet. Again, it's the relative motion that's important. Now, by the way, briefly before I mentioned this galvanometer, this galvanometer is going to measure our electric current, or at least a change in the electric current. So don't worry about how different this is from a ammeter, it's really not that much different. It actually has some magnets behind the scenes to get it to work, but I'm not really going to go over that. So here's a couple examples you can think about. If you plunge this magnet into this loop in this direction, you can imagine the current will go one direction. If you pull the magnet out, it will go the other direction. Notice that if the magnet is stationary, it's not going to produce any current, but only when the magnet is moving is there current. So same would go for a loop, and you're pushing it through a horseshoe magnet. So we could rewrite Faraday's law for this particular case, where the area and the angle are constant, but the magnetic field is changing in time, as minus dB dt of A cosine phi. I will perform this example in a later video, where we look at Faraday's law of induction. Here's a nice application of Faraday's law, a pickup coil in an electric guitar. Notice that here is a depiction of a guitar string, and notice that there's a small portion of a string that's magnetized. Notice that when you vibrate that string, this magnet was going to vibrate back and forth, and we have a magnet with a pickup coil around it, and as a guitar string vibrates around, you're going to change the electrical signal in this pickup coil, and that's going to go to the amplifier. So that pickup coil uses an electric guitar as part of Faraday's law. The coil is placed near that vibrating string, and that portion of the string becomes magnetized. When the string vibrates at some frequency, the magnetized segment produces a changing flux through the coil, and the induced EMF is fed into an amplifier. And that is interpreted as an electronic music note. Okay, so this is a nice application. By the way, electromagnetic induction has many, many useful applications. So I'll mention a few in this lecture and subsequent lectures. Let's look at methods 2 and 3 of inducing EMFs, namely changing area and changing area orientation. So method 2, change the area of the conductor, or coil, in time. Here's an example. Suppose you have a bar here, and suppose you have rails, and those rails, let's say, are conducting and the bar is conducting. So the bar is in electrical contact. And as the bar moves along, there is an increase in the areal extent of the magnetic flux. That is to say, if this was the original area, as the bar moves along from this dash position to this new position, notice that it's moved a distance delta x, and now, since the area is greater, we're going to produce an EMF. And by the way, since we produce an EMF, if there's a resistance, an EMF will manifest itself as a current, that is I. We recall Ohm's law for ohmic resistors, that I is equal to EMF divided by R. That is the voltage divided by the resistance. Okay. So by the way, this kind of setup is very similar to my knowledge about how railguns work. I don't know a whole lot about railguns, but that's the basic idea. And how about number 3? What if you change the orientation of the coil in time? So here's a good example. Suppose you have a crank flashlight. You turn a coil by mechanical means with your hand. The coil is moving through this strong magnet. There's carbon brushes here, and you're going to get current that is registered. So if you mechanically rotate a coil, you change the perpendicular angle, the orientation of phi, thus changing the flux through the coil. Okay? So these are all ways to generate an EMF and thus a voltage. By the way, there's an interesting way to generate an EMF in a conductor, a strong conductor, that's moving through a magnetic field. Let's walk ourselves through this. Suppose we have a conductor that's moving with a velocity in a magnetic field. Notice that charge carriers in the conductor experience a force of magnetic force QVB. Why is that? Well, if the velocity is to the right, and if the magnetic field is into the page, you can imagine there's a bunch of free charges, or at least loosely bound charges on that conductor. So that's essentially QV cross B, and the thumb points upward. So positive charges should collect toward the top of this conductor, whereas negative charges should collect toward the bottom of this conductor by just the opposite direction of the magnetic force. Okay? So the resulting charge separation creates an electric field in the conductor. E vector increases as more charge flows. So the faster you pull this, the more charge separation, or the stronger the magnetic field, the more charge separation. Notice that these are going to be like what we call often eddy currents when they're at equilibrium. And by the way, we note that there's an electric force that's Q times E is equal to QVB. That is, the electric force is equal to the magnetic force. So if you divide out the Q, E equals V times B, which is a relationship we've seen earlier in this course, that newtons per coulomb is equal to meters per second times Teslas. Well, let's see what happens over time. So you can imagine that the charge flow continues until the electric and magnetic forces balance. For a positive charge carrier, the upward magnetic force equals the downward electric force. And it turns out that a potential difference will be maintained. So this change in direction would cause a change in polarity, and this is sometimes called the Hall effect. Now, by the way, that's with a single piece of conductor. Previously, we were looking at a bar moving on these conducting rails, and once that charge separation got going, the current would actually start flowing. And it turns out that positive charge carriers still move up, negative charge carriers move down, but the wire would have some resistance, and you could imagine that you create a circuit, not a separation of charge. I'll talk more about some of these concepts as we go on. Now, by the way, as we have seen, let's say a little bit more about method 2. One way to induce a current is change the area of a circuit immersed in an external magnetic field. So here's a more technical diagram. Suppose this bar has length L. Suppose the magnetic field has magnitude capital B. Suppose the velocity right now is V vector. Suppose the magnetic force opposes the applied force motion. It turns out that will always be the case, at least as long as there isn't magnetic force being produced. One way to think about this is that there's going to be action-reaction. When you apply a force to the bar to try to move it along the rails, the reaction force is the magnetic force. By the way, there's a deeper reason that there's magnetic force exists. That's because the current in this case would be running counterclockwise. And if the current is upward in this this bar that's sliding along the rails, you could point your fingers upward. This is right-hand rule 1B. That's IL. You cross B, that's into the page, and the thumb points to the left. That's the direction of the magnetic force. Now you may ask the more deep question, how do you know that I is going counterclockwise as opposed to clockwise? That I will go over later in this lecture. But as the bar moves, the area of the circuit increases, thus increasing the flux. Work is done by the applied force, and that becomes internal energy dissipated of the resistor R. And let's assume that the angle between the magnetic field and the velocity is exactly 90 degrees. So you can derive the EMF from the time derivative of the area. This is actually pretty easy to do. One thing you can say is well, that d phi subscript b dt is going to be the time derivative of BA. But B is a constant, so move that out front. So you have the time derivative of the area. But the length is not changing. Only the x position is. So you have B times L times dx dt. But dx dt is the change of x with respect to time. That's just horizontal velocity. So you get this equation, which is motional EMF. EMF that arises from this bar moving along at a constant velocity is BLV. And even if this velocity is not constant, at the moment you know the velocity, you know the motional EMF at that moment. So notice this is a voltage coming from taking a magnetic field strength, multiplying by the length of a bar, multiplying by the velocity that the bar is moving. What about the direction of the induced current? Now, the direction of the induced current is actually going to act to resist the change of the magnetic flux. I'll say a lot more about that in a moment. But right-hand rule 1 for currents indicates counterclockwise current. Again, if the electric current is upward, remember that's the conventional current, the Franklin convention, sort of positive charges. If positive charges are running upward, we perform right-hand rule with the cross product of magnetic field into the page, the magnetic force is to the left. Also, this current produces a magnetic force that resists the motion of the bar. Okay, I hope this is making some sense. So I will perform this example where we actually put some numbers into one of those bars sliding on rails in a later video. By the way, we almost always assume that this bar slides on these rails, but it doesn't have friction. Now, in reality, in real experiments, of course, it must have friction, but we'll usually ignore that. Here's a nice application of Faraday's law, swiping a credit card, okay, with its magnetic strip. So a credit card has a magnetic strip on the back that has regions of alternating magnetization. And by the way, the magnetization there of your particular stripe indicates your identity. When you swipe the card, you move the strip through the circuit of the card reader. So when you swipe it, you're producing electromagnetic induction. By the way, did you ever swipe your card too slow? It doesn't work, right? Turns out that you're not getting enough voltage, you're not getting enough signal. Different parts of the strip have different fields, so the motion of the strip causes a series of flux changes that induce currents. The pattern of magnetization of the card determines the pattern of the induced currents. And so the card is red. Basically, you're taking a group of magnets, which identifies you, swiping it through a machine, getting a certain electric current signature, and then that tells the card reader that you want to pay for your item. Simple as that. Notice that certain things in this world seem so mysterious about how they work. Essentially, that's it. It's just magnets and you swipe them through. Electromagnetic induction. Now, by the way, you may ask, what about the more modern cards that have the chip in them? Okay, so I'm not an expert on the chip technology, but as far as I know, that's a small microprocessor. So it's going to be read in a different way. The chip itself is more secure. It connects more directly to your bank, etc., etc. So it's not as simple as swiping a card, so it's a higher level technology. Okay, how about changing magnetic flux loop area orientation with time? In other words, what about the angle between the area vector and the magnetic field? Well, let's first define phi as omega times t. So if phi is going to change its orientation, you can imagine omega is going to be like an angular velocity, and then t is going to be time. Let's let phi be in units of radians, so that omega is in radians per second and time is in seconds. So suppose we look at Faraday's law here, and suppose it's many coils. So we have minus n d phi sub b dt is minus nba, b, the magnetic field, and the area of the loop are not changing, but we need to take the time derivative of cosine, omega t. Now, many of you who are calculus wizards know how to do this. The time derivative of cosine omega t should be minus omega sine omega t. So two minuses make a plus. So we should get what we often refer to as the electric generator equation. In other words, if you have multiple loops and the angle of the area of the coils is changing with time, that is, it's rotating, this is going to be the equation that tells you what is the induced voltage. So it's NBA omega sine omega t. By the way, you may ask, can you put cosine omega t there? Sure. But notice that I'd choose sine omega t if at time 0 there's no EMF. I would choose cosine omega t if at time 0 we're at the maximum EMF. Remember, the sine function begins at 0, whereas the cosine function begins at its maximum amplitude value. So I will perform this example also in a later video, where we calculate the maximum EMF of a typical United States electric generator. Okay, here's a nice application of Faraday's law. What if you turn a crank, and it's a crank flashlight? So as I already showed a couple slides ago, you're turning a little coil inside of there. So you turn that crank, it rotates a coil of wire in the magnetic field of a permanent magnet. If the switch is off, there is no current and there's no opposing magnetic force. So it's easy to turn. But once you turn it on and you try to produce light on this flashlight, since there is an opposing magnetic force, so remember, when you rotate this thing, there's going to be a force on the loop to resist the change. Again, you can't get energy for free, and when we consider Newton's third law, when we try to push this loop in a magnetic field, the loop kind of pushes back on us. So you must do rotational work to keep the crank turning. This is the source of the light in the circuit. Now, commercial electric generators use a much larger version of the same principle. Again, a modern electric generator is a coil turned in a very strong magnet. Okay? And then what is produced is alternating current. Okay. So let's have a look at a few more applications. Here's a shake flashlight. You take this flashlight and you shake it back and forth. Notice that this coil moves forward and back. And then notice that again, that's electromagnetic induction. You charge the batteries temporarily. And it's not even really so much a battery. The real batteries are not necessary. You charge something, like a capacitor maybe, that stores charge temporarily, and you can run this flashlight. Look at this, the turning blades of a wind turbine. The turning blades of a wind turbine turn a coil, and that coil turns in a magnet, and that magnet induces a current, and that current is AC and fed out to the electrical grid. This change can So the turning blades rotate a coil of wire in a magnetic field in this wind turbine. This change induces enough current to power many homes. Typically, one of these industrial strength wind turbines can easily power 1,000 homes if it's running at its capacity factor, at its maximum ability to produce electric power. Okay, let's shift gears a little bit and let's talk about Lenz's law. So Lenz's law, in my opinion, is the cheapest way for someone to ever get their name on an actual equation or a law. Because basically Lenz's law is just the minus sign of Faraday's law equation. It basically tells us the direction that things move. So what is the direction of the induced current in a coil? Any induced current will induce a magnetic field. Lenz's law says the polarity of the induced EMF in a conducting loop produces a current whose induced magnetic field is directed to oppose the change in magnetic flux through the conducting loop. The name of the game here is resist the change. Always resist the change of the magnetic flux that's changing in time. So Lenz's law is a fancy way to state the conservation of energy. That's the reason there's a minus sign in the Faraday's law equation. Suppose you have a permanent magnet is moved into a coil, and there's current in the coil. Well, why is that? Because these coils are going to produce their own B field, which oppose the changing magnetic flux with time. So, if you move that magnet to the right through these coils, you'll increase the magnetic flux, and we increase the magnetic flux in these coils. The coils are going to produce their own magnetic field, which is in the opposite direction, to oppose the change or resist the change. So notice, as viewed from the left-hand side, it would look like, by right-hand rule 2, that if we point our fingers in the direction that the current is moving, the thumb points to the left. In other words, you can imagine the current is running counterclockwise as viewed from the left-hand side. Now notice, here's an important point. Again, it's always going to be resist the change. Now I often like to explain it this way. Think of coils like lazy roommates. I don't know if any of you watching this have lazy roommates. Maybe they sit on the television all the time and play their video games all day. They never stop. I mean, they've always got Fortnite on. I guess that's what the kids are playing these days in the year 2020. But in any case, the idea is that if this is a stubborn roommate, the stubborn roommate never wants to change. The stubborn roommate always resists change. So if you personify the loop themselves says, hey, I don't like change. If you have more magnetic flux through me, I'm going to push back on you with magnetic field that's in the opposite direction. So if you're increasing the magnetic field will be to the left to resist that change. But notice that if you were to pull the bar magnet out, the stubborn roommate says, hey, I already had magnetic field lines in there. Don't change anything. So these coils would act to reinforce in the direction that B was already in that direction. I'll show several more examples of this, but start thinking about Lenz's law. So here's some examples of Lenz's law. Suppose you have a magnet and you're going to plunge it down through this loop. Okay? So when you do that, okay, there's electric current on the loop, but notice that the electric current acts to resist the change of the magnetic flux. So moving the magnet downward increases that downward flux. Notice that there's going to be coil, conventional current, that runs counterclockwise. And if we point our fingers in the direction of that counterclockwise current as viewed from above, the thumb points upward, and that's the direction of the induced magnetic field. So again, the loop needs to generate an upward pointing field to oppose this change. A counterclockwise current is needed to induce the upward pointing magnetic field. Now, what if the bar magnet is moved upward? If you move the bar magnet upward, the loop will tend to reinforce magnetic field that originally was pointed downward. So again, the idea is that always think of your loop as a stubborn roommate. Never wants anything to be different, always wants to resist the change. So if you take that same bar magnet and pull upward with a sudden velocity, so the magnetic flux is changing in time, you're going to have the current running clockwise as viewed from above. Because clockwise, as viewed from above, has an induced magnetic field that's downward. So again, think of loops as producing their own sort of imaginary bar magnets. Because again, you start pushing bar magnets into loops, loops themselves produce their own electric current that has sort of this north pole repelling this north pole. The induced current tends to keep the original magnetic flux through the loop from changing. And that's the name of the game. Okay, I hope you're starting to understand Lenz's law. Now let's have a look at Lenz's law through an example here. And typically conceptual examples I will work out on these slides. So I'm going to do that on this set of slides. So here's an example. A coil is moved through a magnetic field as shown below. The field is uniform inside the rectangle and zero outside. What is the direction of the induced current and direction of magnetic force at each of the positions shown? Okay, so let's have a look at this. Notice that I think we can start off as simply as possible by saying here at point A, the EMF and thus the current should equal to 0 because I think there's no magnetic field. Also at point E here, there should be 0 current because there's also no magnetic field. So there can possibly be no magnetic flux. Now let's look at point C. Around the vicinity of point C, there's magnetic field lines, but the magnetic field lines are not changing in time. There's not more or less magnetic flux. Let's assume this magnetic field is everywhere uniform and everywhere equally spaced. So the current will also be 0 here because again, d phi subscript b dt is equal to 0. All right, but now let's look at lowercase b and lowercase d, respectively. Let's start with lowercase b. When the loop moves onto the scene from no magnetic field location to magnetic field location, I think we are increasing, so we're increasing the magnetic flux that is out of the page. So this magnetic field is out of the page. So again, think about this loop as your stubborn roommate. They say, hey, I don't like magnetic field out of the page. I like things being like 0, like they were originally. So it's going to produce its own electric current that resists the change. That is, it's going to have electric current that has magnetic field going into the page, not out of the page. So I think the current is going to run clockwise. So it's going to be something like, something like so. So this is going to be the direction of the electric current. Okay, so that's the electric current. Now how about at D? At D, hopefully you can almost intuitively induce that it's going to be the other direction. Instead of clockwise, it's going to be counterclockwise. And indeed it is counterclockwise, but let's see if we can verify that. Well, at this point here, we're decreasing. So we're decreasing the phi sub b, the magnetic flux that's out of the page. So if we're decreasing the magnetic flux that's out of the page, the loop says, hey, I don't like anything to change. I want to reinforce that magnetic flux that goes out of the page. So now our thumb points out of the page, and then the current should cycle through counterclockwise. Okay, now here's an interesting thing though. We ask not only what is the direction of the induced current, but also maybe are there any forces on these loops? Now think about this. Notice that even though these are circles, you could think about them as loops having 1, 2, 3, 4 pieces to them on sort of their north, south, and east and west places. North, south, east, and west places. And that's only because I think there's going to be some symmetry in how things are going to cancel. So consider both the north and the south pieces of this loop. The north one, it's moving to the right. The magnetic field is out of the page. So the magnetic force here will be downward. But notice on the bottom here, the current is to the left. The magnetic field's out of the page. The magnetic force is going to be upward. Notice these two will exactly, because they're the same length, they will cancel. Notice over here, again, to the left, out of the page, so it's up. So right here, the magnetic force is up. And then right down here, the magnetic force is downward. Okay? That's both based upon right-hand rule 1b. Notice the current is going to cancel on those places. Now imagine when this thing is moving onto the scene. There is electric current on the left-hand side, that's the west side, but on the east side, there actually is magnetic field, but there is no magnetic field over here. So there's no magnetic force on the left, but there is a magnetic force on the right-hand side. So if we point our fingers down, the magnetic field is out of the page. This magnetic force should be this way, F sub b. Now notice also, this portion of this loop right over here on the right-hand side, that's the east side, will have no magnetic force. But then this one being down, notice that down again, and then out of the page, left. So the magnetic force here is also to the left. So we get a very interesting result. We get the concept of what we often call magnetic braking. So why do we call this magnetic braking? Well, it's because the magnetic forces are, suppose there's a velocity here. This loop, as it moves on, should slow down. There's a magnetic force that opposes the velocity of the motion. Moves over the magnetic field, and then as it moves off this magnetic field, it also slows down. So again, this is often called magnetic braking. So you can't get energy for free. It's harder to push a magnet into many coils because of the induced magnetic force. Now, by the way, now that I've cleared all the writing here, I want to also mention one last thing, and that is the following. If instead a coil is going over a conductor as opposed to a magnetic field, the eddy current is going to cause repulsion, and that's going to cause magnetic levitation. Think about this. If you've got a conductor down below, that conductor is going to have charges that are going to move to different poles. We saw that before when we had the conductor, which had that Hall effect. But it turns out, if instead the coil is over a conductor, the eddy current, that is the actual rotating current in the conductor itself, will cause repulsion of these coils, and that's going to be like a north magnet facing a north magnet. But that actually allows the coil to levitate above, and thus we get the concept of magnetic levitation. Now, I will tell you that you've all probably heard of these magnetic levitation trains. There's several installed around the world. There's a few in China and several other places in the world. Those magnetic levitation trains basically use this magnetic braking process, and they use this magnetic levitation process. In fact, let's look at those eddy currents here briefly. So notice eddy currents are induced when a metal sheet is pulled through a magnetic field. Notice that if we pull the metal sheet to the right, the velocity is to the right, the force of the pull is to the right. Notice that what's going to go on? Well, you've got charges moving to the right, and the magnetic field is from south to north, okay? So the magnetic forces are going to oppose the direction of this motion. How do we know that? So what we're saying is this. If you take this conducting sheet and pull it through this strong magnet, notice that there's going to be current, that is electrical current, in the sheet itself, which is going to tend to, by Lenz's law, resist the change. Notice that previously there were magnetic field lines moving from south to north over this region. But suddenly when we pull, we're going to have electric current that is induced in a direction to resist the change. So instead of south to north, the electric current is running, let's see, clockwise as viewed from above. So that's going to be a north magnet pointing down as opposed to pointing up. Okay? So that's the idea. Notice that over here, this part of the metal sheet had roughly more or less no magnetism on it, but now it suddenly has a south to north going that way. Well, it's going to also produce its own magnetic field to resist the change. Okay, so again, I should have actually said the magnetic field lines are going to go out of north into south. Sorry about that. So if they're going to go out of north into south, then this one's going to be just the opposite direction. It's going to be counterclockwise. Why is that? Well, this north to south needs to have its magnetic field resisted by this current. So again, right-hand rule, and then that's the direction of the magnetic field. Now notice, because we have electric current going down over here, and because we have electric current going up over there, so in the end, here's what we'll have. We'll have electric current going this way, and we'll have electric current going this way through the center. The electric current will both be going the same direction through the center. So if the electric current up here is like so, sort of going up this sheet, we perform IL, that's the electric current, cross B, that's north to south magnet there, and the magnetic force is to the left. So notice that if you pull a sheet of conductor through a uniform magnetic field, you produce these eddy currents, and they're basically circulations of electric current due to Lenz's law. The magnetic force due to the eddy currents will be a retarding force against the direction of the velocity and the pull force. The eddy currents are a form of magnetic braking. So this is the last thing I want to say about Faraday's law and Lenz's law. So thank you very much for your attention. So if you like this content, please smash that like button and also subscribe to the channel in order to grow the channel. Please share this content amongst your social networks. I look forward to reading your comments, and I want to thank you for watching High Peak Education. I will see you in the next video.